Discover the art and precision of building and installing bridges and roads, connecting communities, and shaping the future. The construction of the North Manama Causeway followed a highly coordinated sequence that combined deep foundation works, precise precast operations, and controlled segmental erection. The process began with the formation of the causeway's foundations using bored, cast-in-place concrete piles. Each pile was created by drilling a long shaft to the required depth and diameter, lowering a steel reinforcement cage into the hole, and filling the shaft with high-strength concrete. Several piles formed a pile group, which was then integrated by casting a reinforced pile cap. This pile cap acted as a rigid platform that distributed structural loads from the piers onto the piles. Once the foundation system was completed, reinforced concrete piers were built on top of each pile cap. These piers served as the vertical supports for the superstructure, providing the mounting surfaces for bearings and precast segments. Specialized bearings were then installed at the top of each pier. These components were custom engineered to allow controlled rotation, translation, and expansion of the bridge deck under thermal and structural forces. The superstructure was formed using a precast segmental balanced cantilever method. All segments were produced in a dedicated precast yard using the short-line match casting technique. In this method, each wet segment was cast in a stationary mold directly against the previously cast segment to ensure perfect geometric alignment. After curing for several hours, the new segment was shifted into the match cast position and later transferred to storage. This ensured that when segments were erected on site, their joints aligned exactly. Two erection methods were used depending on location. For ramp structures, heavy crawler cranes lifted the segments into place. For the main bridge spans, a launching girder positioned each segment with precision above the piers. At each pier, the segment was lifted, aligned, and its match-cast faces coated with epoxy. Temporary post-tensioning bars were installed and stressed to hold the segment during erection. Balanced cantilevering was essential. A new segment added on one side of the pier had to be matched by a corresponding segment on the opposite side to maintain structural balance. As segments accumulated, permanent post-tensioning tendons were threaded through ducts and stressed from one end of the cantilever to the other. This provided the structural continuity and strength required for long spans. When two completed cantilevers from adjacent piers approached each other, a closure joint or link slab was cast at mid-span to form a continuous deck. This process was repeated across all spans until the entire bridge deck was completed. Traffic management was carried out in 9 stages. Temporary diversion roads were first constructed outside the existing Al-Fateh Highway to allow safe access for pile, pier, and deck construction. Continuous quality control accompanied each stage, including concrete tests, soil compaction checks, and independent laboratory verification of materials. Environmental controls minimized noise, dust, and marine disturbance near the coast. Through this systematic sequence from piling to segmental erection and final closures, the North Manama Causeway was completed using a fast, safe, and precise construction process tailored to Bahrain's coastal conditions and traffic requirements. The Tema Port expansion project marks an unprecedented development in sub-Saharan Africa, representing the most ambitious port construction on the West African coast. Initiated by Meridian Port Services, the project has progressed through major milestones, including extensive land reclamation, breakwater construction, and the installation of advanced ship-to-shore and RTG cranes. With new quay walls, container yards, and modern service systems completed, the expanded port is now prepared to go live, strengthening Ghana's capacity for future maritime trade. The Primava Camilo Sea project is a key infrastructure initiative designed to strengthen the connection between Antioquia and Colombia's Pacific coast. Led by Pavimentos Colombia SAS, the project involves building the second carriageway along the Primavera-Amaga corridor up to the Camilo Sea sector. Its scope includes 6 bridges, 2 tunnels, and approximately 5 kilometers of new roadway. Construction requires moving nearly 1 million cubic meters of excavation and installing around 100 linear meters of retaining walls. A major highlight is the use of post-tensioned bridge girders, some cast in situ and others assembled externally and launched into position. The project also features long-span bridges, including segments reaching up to 250 meters. Additionally, the 2 tunnels pass beneath the Medellin-Cartago pipeline, demanding precise engineering. With high-performance concrete ranging from 2,500 to 6,000 psi and a dedicated supply fleet, the project stands as a strategic component of Colombia's Prosperity Roads and the Pacific 1 and Pacific 2 concessions. The Bicester Bridges project is a landmark infrastructure initiative designed to support Oxfordshire County Council's vision for new housing and employment growth in the Bicester area. Led collaboratively by the Council, Network Rail, and Story Contracting, the scheme focuses on delivering 2 new underbridge structures that unlock agricultural land to the north of the town and pave the way for the future A4095 route. The project includes a reinforced concrete pedestrian underpass and a larger concrete and weathering steel highway underbridge carrying the Chiltern twin-track railway line between Bicester North and Banbury. Works commenced in September 2020 and followed a 7-month program of preparation, fabrication, and on-site wet pour construction. Both structures, weighing a combined 100 tons, were built offline to avoid disrupting rail operations. During Easter 2021, a planned 100-hour possession allowed the team to remove track, excavate 21,000 tons of earth, and carefully drive the bridges into their final positions. This successful installation, followed by extensive backfilling and track reinstatement, demonstrates a model of proactive collaboration and engineering excellence that will enhance mobility and development opportunities across Bicester. The installation of the precast concrete box culvert begins with clearing the project area, which, at first, resembles a dense jungle. Crews remove all vegetation, brush, and debris to create a workable construction zone and to expose the existing creek channel. The original culvert is already in place, and because it has just rained, the water flowing through the creek is muddy and unstable. Since the new box culvert is designed to be 65 feet long and 16 feet wide, large enough to fill the entire creek bottom, full site preparation is essential. Once visibility is improved, workers continue knocking down remaining weeds and obstacles near the stream alignment to establish a clean and unobstructed workspace. The next major step is installing a bypass pumping system. Because all in-stream work must occur in dry conditions, the crew sets up a high-capacity pump to divert flow around the culvert site. This pump operates continuously, 24 hours a day, to keep the work zone dry. Water is pumped upstream, routed through hoses, and returned downstream along the natural creek bed, ensuring that activities inside the excavation remain unaffected. With the bypass in operation, excavation begins for the new box culvert structure. Workers dig a deep, wide trench following the designed alignment, carefully shaping the grade to accommodate the culvert base. At each end of the excavation, they install dewatering wells packed with stone. These wells help control subsurface water pressure and prevent the stone foundation from becoming saturated during installation. The large concrete cutoff walls, critical components that prevent water from undermining the culvert, are also positioned and aligned within the trench. As soon as the foundation and layout are complete, the crew prepares for the arrival of the crane, which is scheduled to lift each precast box section into place. Crane setup is a major operation. Multiple truckloads of counterweights arrive, and the crane operator works with the crew to configure the machine for heavy lifting. Because the delivery of all box sections and their installation are planned for a single day, timing is crucial. Any delay would halt progress for weeks due to contractor schedules. Once the crane is ready, trucks begin delivering the precast culvert units. Each section is rigged, lifted, and precisely set into the excavation. Workers guide the pieces into place, joining them sequentially to form the continuous 65-foot structure. Proper alignment is checked at every stage to ensure a tight fit and smooth internal flow path. After all sections are installed, the wing walls are assembled and secured to stabilize the inlet and outlet areas. Backfilling operations follow. Crews place and compact soil around the culvert, rebuild the embankments, and restore the natural creek contours above the structure. Finally, they clean the site thoroughly, spread grass seed, and apply mulch to promote vegetation regrowth and prevent erosion. With the wing walls finished and the site restored, the box culvert installation is officially complete, marking the successful end of the project. The launching of precast girders using an overhead beam launcher is a highly coordinated construction operation designed to place heavy bridge beams accurately across consecutive spans. The process begins with the jointing of the main truss modules, where individual truss sections of the beam launcher are aligned and securely connected. This step ensures the launcher attains the required structural rigidity, allowing it to support and transport massive precast girders safely during installation. Next, the crew performs beam trolley rail track preparation. Workers position and level the rail tracks on top of the launcher's truss structure, checking alignment and elevation to guarantee smooth trolley movement. Proper rail preparation is essential because even small deviations can lead to unsafe loads or hindered travel. Once the launcher is ready, precast beam transportation begins. Heavy-duty trailers move the concrete girders from the casting yard to the erection site. Upon arrival, the beams are positioned under the launcher and lifting tackles are connected. This step transitions into the beam feeding and lowering operation, during which the beam trolley hoists the girder and slowly transports it along the length of the launcher. Operators guide the beam precisely until it reaches the intended span. The girder is then lowered gradually onto the bearing pads, ensuring correct seating and alignment. After the girder is fully placed, the crew completes all checks, marking the first span done. With the initial span successfully launched, the equipment must be repositioned for the next phase. This involves reversing the beam launcher for dismantle, where the launcher is carefully moved backward, its systems reset, and some temporary components disassembled to prepare for shifting to the next span, or for complete removal depending on the project stage. Through meticulous planning, synchronized teamwork, and precise equipment operation, the overhead beam launcher enables fast and safe installation of precast girders, enhancing efficiency in modern bridge construction. Using the full-span launching method, the 400-ton precast span is carefully lowered from the launcher to its final position. The operation is carried out gradually to ensure controlled descent and structural safety. Throughout the process, the surveyor continuously verifies levels and alignment, confirming that the span settles precisely within the required tolerances. The world's first Kiloton bridge girder erection machine has been deployed in Fujian province to install massive girders for the Maza Bay Cross-Sea Bridge, a key part of the Fujian high-speed railway. Measuring 40 meters in length and weighing more than 1,000 tons, this advanced machine enables precise lifting, positioning, and placement of each girder over the wide sea channel. Its automated control system ensures stability and efficiency throughout the erection process. Thanks to this equipment, construction progress has been significantly accelerated, supporting the railway's goal of beginning operation in 2022. The nighttime lowering and installation operations for the Brianza overpass were carried out near the interchange, with activities extending past midnight to minimize traffic disruption. The steel-concrete composite deck had already undergone an initial translation from the assembly area, where it was fully prefabricated. Mounted on multi-axle transport carts, the 250-ton deck was moved along the roadway up to the junction, reaching the designated insertion lane. Here, a delicate 90-degree rotation was executed to align the span with its final position over the SS-36 highway. Once the rotation was completed, The deck was again repositioned on the transport carts and brought close to the abutments, where the final lifting operation would take place the following day. To safely handle the weight and geometry of the 44-meter-long structure, the SS-36 highway was closed to traffic starting at 2100. A lifting team consisting of 3 cranes, one rated at 750 tons, one at 500 tons, and one at 300 tons, was mobilized to execute the hoisting phase with full redundancy and stability control. The new bridge features a 15-meter-wide cross-section, housing 2 3.25-meter traffic lanes, 2 1-meter shoulders, a 2.5-meter cycle pedestrian path, and a 1.7-meter sidewalk. The steel deck comprises 2 variable-depth edge girders up to 3 meters high, connected by 70-centimeter crossbeams, above which a 25-centimeter reinforced concrete slab will be cast. Designed to support 2 heavy vehicles of 108 tons each, the structure also provides an improved clearance of approximately 5.20 meters compared to the previous 4.45-meter underpass. The construction Viaducto Os Portos demonstrates a highly advanced approach to elevated railway infrastructure. The viaduct is built using the TC4000 high-load tower system, which provides robust temporary support capable of handling the significant weight of precast segments during installation. These towers are strategically positioned along the viaduct alignment to ensure stability, allowing safe and efficient erection of each span. The County Route 24-meter lattice system is employed to span the gaps between towers. This system facilitates the placement of long precast segments, maintaining precise alignment and level across the entire structure. The modularity of the County Route 24 system allows rapid assembly and disassembly, which accelerates the overall construction schedule while reducing on-site labor requirements. During construction, each precast segment is lifted onto the lattice system and carefully adjusted before being joined to the previously installed spans. This method ensures continuity and structural integrity, minimizing the need for extensive temporary supports on the ground. Surveying teams continuously monitor alignment and elevation to guarantee compliance with design tolerances. The combined use of the TC4000 towers and County Route 24 lattices exemplifies a modern approach to viaduct construction, integrating safety, precision, and efficiency. This methodology is particularly suitable for high-speed rail projects, where maintaining exact track geometry is critical for operational safety and passenger comfort. The Chenab Bridge, a marvel of modern engineering, stands as India's highest railway bridge and the world's tallest arch railway bridge. This extraordinary structure is the first in India designed to withstand contact blast loads and an earthquake of intensity 8 on the ROR scale. Its strategic location in the young Himalayan mountains exposes it to extreme natural conditions, including gale-force winds. The bridge is engineered to allow trains to safely traverse in winds of up to 90 kilometers per hour, while sensors automatically trigger signals to stop rail traffic if wind speeds exceed safe limits. The foundation of any bridge determines its strength. And for the Chenab Bridge, constructing foundations was a formidable challenge. The Himalayan terrain posed serious technical difficulties, necessitating extensive slope stabilization before the bridge piers could be erected. The piers themselves are extraordinary. The tallest reaches a height of 137 meters and rests on a massive foundation measuring 36.5 meters by 50 meters. The bridge spans a deep gorge with extremely steep slopes, varying from 43 degrees to nearly vertical 77 degrees, making slope stabilization a Herculean task. Before construction began, elaborate geological tests were conducted to assess rock mass stability. The Indian Institute of Science in Bangalore designed the slope stabilization measures, which were subsequently reviewed and proof-checked by the international consultancy firm URS. Once the designs were finalized, preliminary site activities commenced, including tree clearing, developing dumping yards, and constructing approach roads on steep slopes to facilitate heavy-duty dumpers and other machinery. On the Buckle side, nearly 5 kilometers of access roads were built, while the quarry side required 3 kilometers. Catch trenches were installed at each stage to prevent excavated debris from falling into the river. Total excavation depths reached 218 meters on the Buckle side and 206 meters on the quarry side. Due to the extreme slope conditions, the top-down construction method was adopted to ensure safety. Initially, the topmost bench was cut and leveled, followed by staged excavation in increments of 3 to 5 meters. Normal blasting was used to remove rock up to 6 meters from the final profile, while precise pre-splitting, involving small explosives in deep holes, ensured the correct slope and prevented damage to the surrounding rock mass. Controlled blasting aided further excavation, after which excavators, jackhammers, dumpers, and dozers removed debris to designated dumping areas. Stabilizing the slopes involved installing rock bolts of various lengths, 4, 8.5, and 11.5 meters, along with weep holes to relieve potential hydrostatic pressure. A layer of shotcrete reinforced with steel fibers was then applied to strengthen and secure the slope. On the Buckle side, more than 40% of slope stabilization work has already been completed. Each construction activity follows a meticulous sequence, as delays can affect subsequent tasks. Logistics are complex, requiring the transport of large quantities of diesel, explosives, and equipment to the remote site. The Chenab Bridge is no ordinary project. Its demanding design, combined with the challenging Himalayan environment, makes it a symbol of engineering excellence. Afcons is proud to contribute to this landmark achievement, constructing a bridge that will safely carry trains across one of the world's most formidable landscapes, setting a new benchmark in railway bridge construction. The Yavuz Sultan Selim Bridge features one of the world's longest inclined cable-stayed structures, spanning 597 meters. The bridge is supported by 8 507 high-strength inclined stay cables, which provide exceptional stability and load distribution across its deck. Each cable has been precisely tensioned to ensure the structural integrity of this remarkable engineering feat. A key highlight of the construction was the application of post-tensioning over a 305-meter section, enhancing the durability and performance of the bridge under dynamic loads. The The bridge's towers rise to an impressive height of 322 meters, serving as the main anchors for the inclined cables and offering both aesthetic and functional prominence. The approach segments, totaling approximately 372 tons, were carefully lifted and positioned, ensuring seamless continuity between the main span and approach viaducts. This combination of inclined stay cables, towering pylons, and massive approach segments demonstrates advanced engineering techniques, allowing the bridge to carry heavy traffic safely while withstanding environmental forces. The Yavuz Sultan Selim Bridge stands as a modern landmark, showcasing the capabilities of contemporary cable-stayed bridge design